Bismillah, salatu wassalam ala Rasulullah. So we're starting the continuation of our ETO selected classifiers. This is the week 6. So we're taking on decision tree the third time. So last week, so we quickly go through briefly what we discussed. So last week, we discussed the idea of decision tree as a follow-up to the previous week, where we also look into example. Yeah, we consider this example, how we can use it to solve a very simple problem. And then we say that the choice of the attribute to be used in partitioning the data, we go a long way to determine how long your model is going to be, or how big the model is going to be, or the time that it's going to take before you finally get the final solution. And of course, that could also affect the accuracy of the model you are building. Because if you choose the wrong attribute, you might end up having a tree that the attribute will finish and not all samples will have been correctly classified. At that point, you don't have option. You just have to make voting to push the remaining samples to a particular class at random based on majority votes. So a situation whereby you still have some samples that belong to both to different classes on the same node, you need to partition for that, but there is no more attribute to partition because you cannot repeat an attribute twice. You can only use an attribute only one time. So if you choose wrong, so the choice of attribute is very important. However, it is allowed for you to choose at random. So this is where we have one of the very popular ensemble made from a decision tree called random forest. This is where you randomly select the attribute that are going to be the starting point, the root node. And when you change a root node, you will end up having different models. Then you let them vote. You build as many randomly selected, you build as many models as possible with the root node randomly selected. So then build as many as possible, and then you can make them vote to decide on your final solution. This was the ensemble method from decision tree, which is often referred to as we call it random forest. Random forest. Random forest is, you have a decision tree, you have a tree. When you have many trees combined together, they form a forest. That's where the name came from. So when you have many trees, you build one tree, you build another tree classifier, then you make all of them to combine together to vote. Then this is what we call random forest. The forest is random in the sense that each of the models get their root node being randomly selected starting node. So we look at it last time. That's okay. Depending on the choice of your nodes, of the root node, you can end up with different. You can see here now we started with refund. So here we started with marital status. So because we changed my status, we are going to have different model. And then you can also start from tax income. So as much as possible, and then you end up, whenever you have the root node that is different, you end up with a totally different model. Now, that's why I said that there could be more than one tree that feed the same data set. Now, so once you build your model through the tree induction that we discussed earlier, so this model now through the deduction process can be used to classify new data sets. So because you have built your model using the training set, whereby you have input and you know the class. So once you train your model, this model now can help you to classify the one that you don't know the output. Of course, since it is testing set, we developer, we have the answer to it, but we will keep the answer away from our system because we want to check if the model we have built is correct or not, or how far is it correct. So maybe out of 1, 2, 3, 4, 5, out of 5 is able to correctly classify 4 out of 5. That is not bad. But then the more data you have, the better for you to be able to train your model and also to be able to judge the classification power of such a model. So we discussed this, and once you build the model, you can always apply the built model to a new case. I will give also example of this, whereby you have, since the model is starting with refund, you say, okay, refund is no. Under refund is no, so you come here. This is the part you are going to take. The next status is marital status. Marital status is married. Here is single or divorced. This is married. So it's going to come here. And at this point, you get to root node. So you don't even need to check the taxable income for this person anymore, because already you use a root node. It means the outcome of this is no. You see, it's no. So this is how you use decision tree to classify. So once you move from the root node, you keep taking the attribute one by one, based on the model you have built. Yeah, if you build your model, if it is this model you are using, then you have to start with marital status. You see here, if we start with marital status, so it will have been no right from the beginning. It means from the root no, we could have gotten that person classified, because you see that the marital status for this case is married. And immediately you start from this one, marital status, anybody that is married, automatically the root node is reached. So that's why I say it depends on the root node that you started with, and that is going to be the basis of our discussion today. How do you decide the appropriate attribute that you should start with? Since starting with any attribute at random can make you miss important information. It could either prolong the decision tree building procedure, or it could even make it to have lesser accuracy. So that's why there are a couple of algorithms that we propose, or method that you can use to judge or to determine which of the attributes you go for. Now, so we also look into the procedure, which we are going to revise quickly. Step one is to pick the variable that gives the best split. We're going to use lowest Gini index. So how do we calculate this lowest Gini index? We see it today, inshallah. Step two is to partition the database on the value of this variable. So you pick the variable that gives the best splits so that you don't choose it at random. So then step three, repeat step 1 and 2. So once you split, you select the best variable that gives the best split based on the lowest Gini index. So then you keep going. So partition the data on the value of that variable. Once you partition, you know you're going to have like 2 partition or over 3, depending on the value of that variable. So to know where should I go next, you have to, at this point, you have to check again. You have to repeat step 1. See, which of the variables should I go for again? You have to keep checking. You have to keep checking until you finish all the variables or the stopping criteria is detected. Now, sometimes you might have to even do what we call tree pruning. So in which case you build so much long tree that some of them are not relevant. We have to cut it off. We have to cut off part of them. Now, so this was where we stopped last time. So we're going to start here today and see how can we use the entropy to really calculate which of these attributes should we start with. This is a kind of, this is a data set that's going to determine based on the given out attribute of outlook, temperature, humidity, windy. We want to decide if somebody should play golf or not. So this is an example of a decision tree built. You started with outlook. You have the 3 possibilities in outlook. You have to look at what are the values of outlook: rainy, overcast, and then sunny. Those are the 3. So you have 3 divisions. Right, immediately you can see here, if you use overcast, you are getting to the terminal node immediately. You get to terminal node quickly, which means outlook could be a very, very better option of starting a root node. So then you have to get further, starting from windy and then continue until you build the total tree. So the algorithm is often called the ID3, which apply a top-down, of course, greedy search through also divide and conquer. Now, the challenge is we have to know that there's no backtracking. Once you use a particular attribute, you cannot use it second time. The major building block of ID3 is what we call the entropy and the information gain, which we use to select the attributes to be used in partitioning the tree. Now, let's look at entropy. How do we calculate our entropy? So, since we know that a decision tree is built top-down, so starting from the root node, and then evolve the partition of the data into subset that contain the instances with similar values. So we want to choose the attributes to divide, that to be used to divide, especially at the root node, that will give us the kind of separating power. You see, you want attribute that when you use it at once, and then you partition it, at least you have some of those samples that will directly get classified, straightforward. Not those that even when you use the attributes, all of them are still mixed up. Some are here, some are here, some are here, because it's not clear where you can partition them to. So the ID3 algorithm uses entropy to calculate the homogeneity of a sample. See, so before you choose an attribute, it tries to check. If I pick this attribute, what's likely going to be the homogeneity? Is it going to result in quick partition of the data into different classes? Maybe I have like 2 classes. Yes or no? Like this, our data set now. It has 2 classes. No, no, yes, yes. If I choose windy, will it give me quickly to get no, and then yes on the other side? Or it's going to mix them together for some time? So if the sample is completely homogeneous, the entropy is going to be 0. So if you get an entropy of 0, then we say that that particular sample is completely homogeneous. It means choosing that attribute could be a good thing for you to go. And if the sample is unequally divided, it has entropy of 1. If the samples are equally divided, it means, for example, now our data is let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 samples. If after this 14, we have 7 yes, 7 no, that they are equally divided. So in that case, you are going to have an entropy of 1. However, if the entropy is 0, it means all of them, they are either yes throughout or no throughout. So that is why we are going to check the sample. Once we divide our data at the root node, some will go here, some will go here. We get here and calculate the entropy for this one. Are all these samples classified, pushed here, are they all belonging to the same class? No, no, no. So you calculate the entropy because you can see it physically. Look at it. You can be able to see it physically as you see it. However, when you have huge data, it might not be possible for you to visualize. Now, so the entropy is used to determine, okay, the samples that are pushed to this side, are they homogeneous or not? If they're homogeneous, that means all of them belongs to class no. Then we stop. It means this is a terminal node. This is how you know this is a terminal node. You don't need to divide it again because everybody there, they belong to the same class. However, if you check the entropy and it's equal to 1, it means, let's say this place, the one you push here, all the samples here, you have no, you have yes, you have no, you have yes. Maybe you have 2 no's, 2 yes. We say this is, they are equally divided. They are not homogeneous. So we need to partition this place again. We look for what we are going to use to partition it. So we have to select the attribute that will give you the correct partition, because when you want to use the attribute now, you don't just want to use it at random. We want an attribute that, okay, we have no, no, yes, yes. Can we get an attribute that will put all yes here and all no here? You see, you do that. Otherwise, if you use a wrong attribute, you might end up having maybe 2, 3 yes and no will still be here, and then 1 yes will come here. It means you still need to work on trying to separate these 2 again, because the aim is at any point in time, we want to maximize the opportunity of separating all the available sample at a particular point in time. Now, so this is where the concept of entropy comes in. So when you have samples, you calculate the entropy, and then you can be able to judge that, okay, all the samples in this particular place, they are all homogeneous. For example, if we start and calculate the entropy for the entire data, and we find out that everything is no, or everything is yes, all the samples, they belong to class no, then there's no need to even try classification. So because we know where they belong. but the entropy will be needed once you divide it one time. So once we divide it here, so we want to see if those samples push here, are they homogeneous? The one push here, now this one is going to have an entropy of, the one going to have an entropy of 0. You can see here, because every sample here, they are all yes. It's going to have entropy of 0. It means we don't go there again. We are done with it. But for these ones, you check it, the entropy is going to be between maybe 0 point something and 1. If it is 1, it means they are equally divided. But if it is lesser, it means one class is more than the other class. And if we run out of attributes, we don't have any attribute to select anymore. Let's say, for example, here, after this level, we push some samples here and we find out that yes, yes, no, no. We have like 2 no's, 3 yes. But we don't have any attribute now. Let's say attribute Wendy is no more there. So in that case, we have to vote. We vote to push all of them. Since we have 3 yes and 2 no's, we say that everybody here belongs to yes. These are some of the places where you have mistakes in the classification. You do that when you are total, you consume all the attributes, and you cannot repeat attributes more than one time. So you can't repeat it twice. It's only one time for each attribute. Now let's see how we calculate entropy as an example. To build a decision tree, we need to calculate the 2 types of entropy using frequency table. There are 2 types of entropy. The first one is entropy using the frequency table of one attribute. Sometimes you have only one attribute. For example, plague of, which is the main thing we were given from the beginning. You see, plague of. This is the main data. We want to calculate the attribute for this. Now, do we plague of? So we want to calculate the entropy to know if they have a kind of homogeneous. That's all of them are yes, all of them are no. If they are the same, then we don't need to do anything. Now, so we say, okay, plague of, this is the formula for entropy. So you are going to sum it over, starting from 1 to C, where C is the number of classes. See, we have yes and no, so 2 classes. So minus pi log 2 to log pi to base 2. So this is the formula. So if you look at this, so we said entropy, you are trying to calculate of entropy of plague of. Should we plague of or not? So which is called 5,9, because we have 5 no's, it has been counted, 5 no's, 9 yes there. So what is the entropy? So entropy for 5, so you are going to have it to be the probability of getting 5 and the probability of getting 9. This is what it means. So the total is 9 out of 9 plus 5, that is going to be 14. So the probability of this is 9 over 14. What probability of this is going to be 5 over 14. So you did the mathematics. So you are going to get appropriately this one and then this one. So the probability of, it means probability of saying no, don't plague off, is going to be 5 out of 14. So you have it here. So once you have the probability, then you apply this formula, which is minus the probability times the log to base 2 of the probability. Then minus is there, this one, because you are adding them together. This is summation. This is summation. But because of the minus here, plus minus, as we were taught, you remember, plus minus will become minus. Then the probability of 9, that is saying yes, go and play golf, and the logged probability to base 2. So if you do this simple mathematics, you're going to get 0.94. So 0.94, you can see, is closer to 1. I said when you have 1, if you remember the rule, if you have 1, entropy is 1, it means it's divided equally. You see, it means you have, it's going to mean that you're going to have the same number of no, the same number of yes. However, it is not equal to 1, but close to 1. So that's why you can see here, no has 5, yes has 9. But if all of them, they all, maybe here I have 14 yes, and this one 0, it's going to give us 0 entropy. So since I didn't get 0 entropy, it means I need to work on this data. I need to divide the data into 2. I need to select attribute. So the second possibility is Sometime now we want to calculate entropy using the frequency table of two attributes. In which case, you want to calculate if you should play golf given outlook. Play golf given outlook. You need to play golf given outlook. Now, so in that case, now it's going to have a kind of one, you have the probability of sunning multiplied by the entropy of 3,2, because here you're going to deal with 2. Because when you select outlook, you're going to break it into sunny. Under sunny, we have 3 yes, under sunny, and then we have 2. Overcast, we have 4 yes. That is, when the weather is overcast, there are 4 people who play yes for the training data we're using. But there is 0 who did not play golf. During the raining time, when it was raining, there were 2 people who play golf, and there are 3 people who did not play golf. So this is what we're talking about here. So that is why you are going to have the probability of having sunny. So what is the probability of getting sunny? Which is going to be 5. Probability of sunny is 5. 5 divided by 14, the total number here, multiplied by the entropy of 3,2, entropy of the sunny here, 3 and 2. So you are going to get that. You know how to calculate entropy. You refer back to this formula. The same thing we did here now. You are going to do here. It means find the probability of 3 out of, because now this time it's going to be 3. Probability of 3 over 2, sorry, 3 over 5. The other probability is going to be 2 over 5. Pay attention to that, because you are dealing with sunny. 3 over 5, 2 over 5. But when we are calculating the probability of sunny itself, it's going to be 5 out of 14. How we get that? So we pay attention to that. So when you don't do again for probability of overcast, which is the second thing, do the same thing. Overcast is 4, probability 4 out divided by 14, times entropy of 40. You are going to see something with that overcast. You see that the entropy of overcast is going to be 0, because all the samples that belong to overcast, they all homogeneous. There's no one that doesn't play golf. And that's what you're going to see here. You're going to get 0 entropy because it is homogeneous. And then you move to the last one. When it is raining, you have 5 out of 14 as the probability of raining. Then you have entropy for 2,3, which is going to be, you have 2 probability, 2 out of 5, and also 3 out of 5. Then use that one, you are going to get this. So finally, this is how you get entropy for the big guy here, this outlook, play golf, provided it is outlook. See, we just calculated the entropy for play golf, given that it is outlook, only one attribute. So whatever you do to one attribute, we are going to do it to the other attributes. And imagine we have 3, we're going to, as you do to outlook, you do it to temperature, you do it to humidity, you do it to windy. You can see the procedure. Yeah. See, however, you have software that's going to do it for you. Just input your data. It compute this thing for you. You will not even realize what has been computed, but just letting you know this is what goes on in the background when you use machine learning algorithm. Now, this is how you calculate the outlook. I mean, play golf given the outlook. Now, once you have done this, now we call something information gain. We're calculating the entropy now for each of the possible partitioning at any point in time. We said the information gain is based on the decrease in entropy after a data set is split on an attribute. Now, after we split, that's decided to select an attribute as, okay, this is the attribute we are going to use. Okay, once you split it, we want to see what is the information gain. What are you deriving from this particular splitting? See? So because constructing a decision tree, as I mentioned earlier, is all about finding attributes that returns the highest information gain. And what do we mean by highest information gain? The most homogeneous branches. So we want to select an attribute that will return the highest information gain for us. And what is information gain? We want an attribute, when we select it, maybe we select outlook. The moment we divide the data, we can see some that are totally classified quickly. But there are some attributes at the first stage, you cannot classify anything directly. You still need to keep partition. Maybe after 2 or 3 steps, then you can get some samples classified while you keep working on others. Now, so this is why to calculate information gain, there are 2 steps. First of all, you calculate the entropy of the target, which we have done before. Entropy of the target, which is the output. That is play golf or not play golf. We did it together. Once you know the entropy of that particular attribute, the next thing for you is to now split the data set into different attributes. You see, we are going to split the data into different attributes. The example I did already for Outlook here. So we have to do that for all the attributes. Play golf, given Outlook. Play golf, given temperature. Play golf, given windy. Play golf when it is humidity. So these data, we extracted them from this original data. See, we extracted this data from the original data. We're just counting when you select Outlook and it is rainy, how many years do you have? When you select Outlook and it is overcast, how many yes, how many no? So those are things we considered, and then we summarize them in this table. So once you bring out for each of the attributes, we have 4 attributes. Now you need to calculate the information gain. You see, information gain for each of them. So now, since we know the entropy of the target, which is 0.94, we calculated it before. Now you need to use the same procedure that I've displayed here, this one. Use it to calculate for each of the new tables, subtables now. See, for Outlook, you see how I calculated it. So I'm going to do the same thing for play golf given temperature. The same thing for this. So this is the gain, this is the gain, this is the gain, and this is gain. Now, so when you do this particular, because we're going to use this formula that is play golf and then Outlook, is entropy of play golf, which we know before, and the entropy of play golf given Outlook, which we calculated before also. So you subtract the 2 together, you're going to have this one. This is the information gain. So the information gain is a negation of the entropy of playing golf, but when you select the particular attribute, that if I break this attribute, if I break my data using this attribute, what am I going to get? What is the information gain? What is the advantage that I'm going to get over other attributes? So if you do that for each of the attributes, this one is getting 0.247, 0.029, this one is getting 0.15, 0.048. See? So in this case, then we are going to go for the one with the maximum information gain. Because it means if I choose Outlook, it's going to assist me to quickly finish up with my partitioning. Then once we select this, so we move on. So step 3 is you choose the attribute with the largest information gain as the decision node now. And then divide the data by its branches and repeat the same process on every branch. You can see. So when I select the Outlook now, because it has the highest information gain, so I go ahead to divide that data. When you have Outlook sunny, these are the samples that falls under sunny, 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 sunny. You can see here, yes, yes. Now you can see overcast, all of them, yes, yes, yes. You can see rainy. You can see no, 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 yes, yes, yes. Now, in this case now, this is the first step, which is this stage here that I showed you earlier. This is the stage here now. See, at this stage now, this is the first step we have carried out. So at this first step, you can see that this overcast is having a very, very homogeneous samples after the partitioning. It means all samples that has overcast as value under Outlook, the Outlook of the day is overcast. So any sample that provides this particular kind of attribute value, we are going to classify automatically as yes. It means we are done with these samples. We are done with these samples. See, we don't go there again. But the other ones, if you calculate the entropy, you can see here, this is 3 years and 2 no's. This is 3 no's and then 2 years. So that's why we are going to, the same principle we use to get to this place, we have to repeat it now, this time around. Then you have to again see that, okay, calculate the information, calculate the entropy, then calculate the information gain. What should I choose? Yes. Now, I've chosen rain, I've used Outlook. I cannot use Outlook again. Now, I have to select from temperature, humidity, windy to see which one has the highest information gain. I go for it. I partition it again. Which one has the highest information gain? I go for humidity. Which one has the highest information gain? I go for windy. Sometimes you might not need to get to windy before you finish, you stop your modeling. For example, by the time we get to humidity, all the data sets are separated. And you can see it in the example here. You see, after leaving Outlook, we went for windy. So we were able to classify everything, yes, no. Humidity, everything, no, yes. You can see that temperature is not yet in. We don't need it. You don't have to use all the attributes. It means by carefully selecting Outlook first, followed by windy, humidity, then we were able to classify all our attributes, all our samples, even without touching temperature. This is the kind of model we want. And it's perhaps due to the fact that we were able to select Outlook with the highest information gain. Now, let me use this to explain a possibility. Now, let's say, for example, that Outlook, let's say Outlook is the last attribute. Assuming that there are some attributes you have used, first attribute, second attribute. Let's say that Outlook happens to be the last attribute that is available to you. We could have this particular kind of situation. You have used all the attributes, and yet you still have a non-homogeneous partitions, which means yes, 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 no, no. 3 yes, 2 no's. All of them yes, yeah, this is correct. 3 no's, 2 yes. This is where in one of the conditions, one of our previous 2 videos, one of the conditions for terminating decision tree modeling is, or algorithm, decision tree algorithm is, if the attribute values are finished, there's no more attribute to use. And yet you are yet to achieve homogeneous at every node. So what do you do at that point? You have to vote. So I'm going to vote here. I say, okay, yes, yes, yes. These are 3 of them against 2. I'm going to say everybody here belongs to yes class. You know, there's going to be 2 errors there. That is the mistake you have to suffer because your decision tree couldn't classify all your system. Here, 1, 2, 3. 3 no's, 2 yes. So we have to vote. Majority carry the vote. We're going to classify everybody here into no. This is if we assume that Outlook is the last attribute that is available for us. There could be a situation that you might face this when you use decision tree. Now, so these are some of the scenarios that are possible when you use decision tree. But for this case, Outlook gave us the best, the best information gain, and we went for it. After that, we are looking for another information gain until we get what we really actually wanted. And if you notice it, you see that temperature has the lowest information gain, 0.029. So, and that is why, but before we get to that one, all our data set already classified. And that was why we didn't have to use it. And it's not compulsory to use it, because the lesser the number of attributes you use before you get your final result, the better. Now, having said that, so these are further examples. See, you can see here, step 4a, a branch with entropy of 0 is a leaf node. So anyone that has entropy of 0 is a leaf node, which means from out overcast we have, yes, I've explained this. But for this one, it has entropy of more than 0, sorry. So yes, 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 no, no, no. In that case, we're going to go down because windy has the highest information gain after Outlook. We go for it first, then we break our data. Then the next one is going to be humidity. We come for it. So the ID3 algorithm is run recursively on the non-leaf branches until all data is classified. So once you have this branch that's purely homogeneous, all of them yes or all of them no, we call them the leaf node. In that case, you don't need to apply anything again. You stop. But other non-leaf branches, you have to continue to do that until all the data sets are successfully classified, or you run out of attributes. Sometimes it happens. The data set are not yet classified fully, but there's no more attribute, and you cannot repeat an attribute 2 times. So in that case, you have to do the voting that I explained, just not like you go on. So another unique thing I would like us to note about this interesting algorithm is the concept of being able to easily generate rules from your decision tree model. See, people see it as an advantage of decision tree. That's why many people like it. Once you build a decision tree model, you can easily generate rules directly from your model. If some of the packages like Weka, Python, they will generate, they have facility to bring out the rule for you. And then you can see example of the one we just built. See, it means that as a rule, rule-based systems are very easy to interpret. People like it, engineering and different fields in medical. If the outlook is sunny and windy, it's going to false, then play golf is yes. Rule 2, if outlook is sunny and windy is true, then don't play golf. If outlook is overcast, then play golf is yes. You can see here the shortest rule. If the moment outlook is overcast, then play golf is yes. Because in our here you can see there every sample that had overcast as value of outlook, the outlook of the day, they all play golf. So you can see one-on-one we can easily transfer our decision tree to become a rule-based system, which is one of the advantages of decision tree, because it's very easy for people to understand what is the outcome of your model. You can put it in form of a rule, unlike some other modeling that has to be buried in mathematics, optimization, quadratic optimization, and so many things you might have. We will look at a couple of them also for those people that are really interested in mathematical background stuffs. However, decision tree, like I said, it's very simple and everybody can relate to it in our day-to-day activities. So when do we use decision tree machine learning algorithm? When do we use it? These are just guidelines. You see, I always say that the best rule of thumb is let the data speak. Don't forget this. Let the data speak. It's very important. So decision tree are robust to errors, and if the training data contains error, decision tree algorithm will be best suited to address such problems. So it is believed that sometimes your data set is having some noises, decision tree will be able to figure them out, because when you build your tree, it will generate some unnecessarily long nodes that you have to cut them later. We call them pruning. So some data sets that are not close to their colleagues, they will be so long in that tree, you just cut them off in what we call pruning. Some other algorithms might not have this capability. If the training data has missing value, then decision tree also can be used, as they can handle missing value nicely by looking at the data in other columns. Yeah, if there are missing value is one of the major problems we face in machine learning. We already discussed missing value before and how to handle it. So when you have missing value, handling it becomes challenging. In fact, if you have decision tree can easily handle that for you. And they are also best suited when the target function has discrete output value. Decision tree are best suited. It doesn't mean we cannot use it when we have to predict numbers like a regression problem. However, the best way to use decision tree is when you are solving classification problem, where the output is discrete, yes or no. As you can see the way it works. When it becomes number, then there's a couple of complications that comes with that. And then finally, we say the pros, decision tree, they are easy to understand. This is one of the things why personally I like it. If I'm developing an application that has to do with clients or people that are not in computing, I like to use it because they can easily understand and they can map nicely to a set of production rules. See, once you generate those rules I show you, people like it. Oh, this is what has happened. Oh, this is how it is considering my data. So because sometimes also we want to carry along the client or people that we developing system for. Decision tree also have successfully been applied in real life problems, so many of them. So good thing is that it doesn't make prior assumption about the nature of the data. It faces their reality, unlike the Bayes, naive Bayes that we're going to see later, inshallah. They are also able to build model with data set containing numerical as well as categorical. If your data is numerical or categorical, they can work with you. So decision tree is one of the models that can, algorithm that can do that. So very powerful in data exploration. You don't really understand the way your data looks like. Why don't you use decision tree? Because it has an inbuilt feature selection. You see, it performs implicit feature selection, which is very important in predictive analytics. What we were doing before, when we were determining which of the features is going to produce a homogeneous partitioning than the other. This is an implicit or indirect feature selection. Unlike other attribute under classifiers, you have to explicitly use feature selection algorithm before you use them. But decision tree on its own has an inbuilt feature selection that it automatically selects the features that are better for your data partitioning. And of course, it can save the data preparation time as they are not sensitive to missing values and outliers. So you can just pick your data and put it into your decision tree. Even though you have missing value, you have outlier, decision tree will deal with them. Outlier will be detected later because the tree will be excessively long. You can cut off those areas in what we call the tree pruning algorithm. You prune them off. So this is one of the very strong points when it comes to decision tree. Of course, everything with advantage also has disadvantages. One of the disadvantages of decision tree includes it doesn't fit well for continuous variable. So when you have continuous variable, so it could result in instability. So it's not a good fit for it, but it works for it, but it's not the preferred option. So although they are very simple when you use them, however, create large decision tree that contains several branches in a complex and very time consuming. So if your data is a little bit big, it could lead to very complicated decision tree that will be even difficult for you to visualize. And also it could get unstable if the variation in data set becomes abnormal. So these are some of the pros and cons that's very important for us to take notes regarding decision tree. It's one of the very good point of call. If you have classification problem, quickly use it and see what you can get. And it's really very much easier to apply and to also introduce to people that are not from the background of AI or mathematics, that doesn't have enough of mathematical background, because it has pictorial representation, as you can easily convert your final model into rule-based system. And everybody in engineering, even at home, in our day-to-day activity, we work with something like this. If you do this, if you read your book, you will get this. If you don't read your book, you will not get this. So it's like a normal way of life for everybody. So if you have a model that you can easily transfer into a rule-based system, I think irrespective of the challenges, it's worth it to give it a try. So I think this is what we're gonna have about decision tree for the day. So once again, so we should thank you for listening, for attending. So we're going to listen to a few questions or comment or reactions in the next few minutes.